Now, let us consider today again another method, that is the interpolation method. This interpolation can be interpolation, the definition of interpolation I need not to say, you must have some idea, you have gathered from your previous knowledge. Interpolation means we are trying to find out the trend of a given set of data. Now, we are finding out the interpolating polynomial. Okay. Here also the same thing, we are having a function that we need to optimize, that is either maximize or minimize, and we will consider the interpolation technique here. How? There are different methodologies available. If we interpolate a quadratic polynomial, then that is the degree of the polynomial is 2, then that is called the quadratic interpolation. If the degree of polynomial is 3, that is called the cubic interpolation technique. Only our idea is, as it is written, that to fit a polynomial to a given function, and not really we are going to find out the optimum value for the function given, rather we will find out the optimum value of the interpolating polynomial, because that is much easier for us to find out the optimal solution. Once again I am repeating basic philosophy behind it. We are given a complicated function and it has been asked that we need to find out the minimum of the minimization, we have to do the minimization of the function, rather the minimum, local minimum of function, or we need to find out local maximum of a function. The function is so much complicated, we are not really able to handle the function. In that case, what we do? We will interpolate the best fitted polynomial there, and our task is to find out that polynomial only. If we fit a quadratic polynomial, that is the quadratic interpolation. If we fit a cubic polynomial, then that is called the cubic interpolation method. Let me tell you how really we are doing it. The methodology I will explain to you, as well as I will explain to you the with the examples the methodology. Let us the function is this one, f x is equal to 20 e to the power x square plus 15 x e to the power minus x square minus 12 x, and we need to find out the minimum of this function within 0 to 1. This drawing of this function I have done with the software Mathematica, and through the Mathematica we have seen that there is a minimum around 0.4, you could see. Okay. Now, there is no negative value as such, as since the range for y has been given from lower value of 15, that is why it looks so that the function is going to the below to the x region, x axis. Okay. You can try it also in with some other software how the function looks like. But if I ask you, why do not you find out the minimum of this function? You can use different method, as you have learned before. You can use the Fibonacci, you can use the golden section, interval halving, anything, exhaustive search you can do. But you see, with the quadratic interpolation, so quickly we will get the solution of it. Now, if I ask you, then what should be the polynomial of degree 2, which is best fitted for this function? How really we will start our journey? We will say that let the polynomial is a naught plus a1 x plus a2 x square. What is unknown to us? Unknowns are a naught, a1 and a2. That is why we need to find out the value for a naught, a1 and a2, which is best fitted to this polynomial. This is the target of us for today's class, to fit a quadratic polynomial to this function, and we will find out the minimum of that polynomial. Now, if this is so, then in the quantitative interpolation we can say that after we are interested to determine the value of a naught, a1 and a2 such that minimum of function f x must be almost same as the minimum of the Px. Px is the fitted polynomial, alright. If x bar is our desired minimum, then that must be very closer to x star, that is the x star is the minimum of the fitted polynomial, alright. And how we can test it? We can just take the ratio of this difference, and if this value is very small, lesser than very small value epsilon, then we can say that the fitted polynomial is accepted. Okay? That is why this is the target of our methodology to fit a quadratic polynomial. Now, you see, we are having a function, that is the function for us, alright. We are interpolating a polynomial, this is within these 2 points we are interpolating this polynomial, say a quadratic function, alright. Quadratic function can be considered as a parabola, a simple quadratic function, and if I just find out the minimum of this polynomial, this is my fitted polynomial Px and this is my given Fx, alright. What we can see that minimum of Px is coming almost here, but minimum of Fx it is expected here. That is why we cannot say that this is my x star and this is my x bar. We cannot say that these are closer, very much closer. That is why this fitting is not accepted at all, alright. We need to find out another polynomial which must fit to this one very nicely. That is our target. That is why what we will all work with Px, we will not do any work with Fx. If we say that minimum of Px is there at x star, then what is the necessary and sufficient condition? The necessary condition would be first order derivative of p with respect to x must be 0 and the second order derivative of p with respect to x must be positive. That is why it has been written here. That is why if we consider the first order derivative of Px, your Px is a naught plus a1x plus a2x square. Then the first order derivative if we consider is coming a1 plus 2a2 plus into x is equal to 0. In other way we can say that x star is equal to minus a1 by 2a2. Okay, that is the important thing we will just use everywhere, that for the fitted polynomial that would be the optimal solution. Okay. And what else we need to check? We need to check always the second order derivative of p, that is coming, if it is positive then a2 must be positive, otherwise it can't possible, it is not possible. In this way we will determine. Now, if we are having a function of this kind where 3 things are unknown, then how many points we need to pass to this function? We need 3 points, then only we will get 3 equations. With 3 unknowns we can get the solution. Let us consider 3 points are given, that is x1, x2 and x3. Generally in the given problem, if the initial interval of uncertainty is a to b, we consider 3 points as a as x1, b as x2 and the middle point of a and b as x3. This is this we consider. Here also we will do the same thing. Just let us see how the algorithm for this. As I said that to fit a second degree polynomial x1, x2, x3, and since we are fitting a polynomial to the function, that is why we will expect that fx1 must be almost same as px1, fx2 is almost same as px2, fx3 is almost same as px3. Since we are considering 2 endpoints, certainly fx1 will be same as px1, fx2 must be same as px2, but the middle point will vary, that is the thing, alright. and from there if these are 3 equations, just you do certain calculations, even by writing a program or by using the software Mathematica also, you can find out the unknowns of 3 where 3 equations are given to you. Otherwise, very difficult to remember this formula. If you can use this formula as well. This has been, we got it after simplification, after simplifying 3 equations, previous 3 equations. Just look at 3 equations, look at this, and from here we found out the value for A0, A1 and A2. Okay. That means we will, if we pass 3 points, then we will get the value for A0, A1 and A2. Okay. Let us try to apply to this function. Let us see what are the values for A0, A1, A2, but you need to know what the algorithm for this function as well. But just by considering 3 points as 0 is the given value, yes, 0 to 1 is the initial interval of uncertainty. That is why 0, 1 and 0.5, if we consider these 3, then you see the functional values there. Okay. If this is so, we will get 3 equations with 3 unknowns. What are the 3 equations and 3 unknowns? Certainly it will be A0 plus A1 into 0 plus A2 into 0 square is equal to 20, and A0 plus A1 into 0.5 plus A2 into 0.5 square is equal to 13.8395, A0 plus A1 into 1 plus A2 into 1 is equal to 36.847, etc. Okay. With these 3 equations and 3 unknowns, we will get values for A0, A0, A1, A2. I will show you what are the values and how we are going to fit the polynomial in the next part. Okay. But before to that, let me tell you the algorithm. Whatever I say that has been given in the algorithm, nothing more than this has been given. That initialize the 3 points, x1 is equal to A, x2 is equal to C and x3 is equal to B, and the what should be the stopping criteria here? Again the question of convergence is coming. If the final interval of uncertainty is smaller, we will stop there and we will declare the midpoint of that final interval of uncertainty as the optimal solution. That is why here also the same thing, since we have considered the left end point as x1 and the right end point as x3, the difference between x3 and x1, the absolute value must be lesser than epsilon. Then we can say we can stop our iteration. If you are not happy with this difference, if you want the difference must be much smaller than this, you can proceed further. Now, for computation of the optimal solution, as I said, x star is equal to minus a1 by 2 a2, and this value we are getting as I showed you. If you remember the formula, if you can remember the formula, just take those formula and substitute, otherwise you do the calculations on your own, that is another possibility. But whatever it is, we will get another x star, that must be in between A to B, but we do not know where x star is situated. It may happen that x star is less than the mid value, that means in between A and x star and A and x2, or it may happen x star is in the right part of the mid value. There are 2 possibilities. If x star is lesser than x2, there again 2 possibilities may happen, that fx star may be lesser than fx2 or fx star may be greater than fx2. If fx star is lesser than fx2, that means we are finding out the minimum of the function. There we can say that there is no minimum in between x2 and x3, because the functional trend value showing that x star is lesser, then x2 value is more, and then fx3, it must be more value. That is why function is unimodal first of all, then only, otherwise not. All right. And if f x star greater than f x 2, very easily we can say there is no minimum in between x 1 and x star, we can eliminate that region. And similarly for the other two cases, if x star is greater than f x 2, but f x star is lesser than f x 2, there is no minimum in between x 1 and x 2, we can just eliminate that. There is no minimum between x 1 and x 2, it is there is no minimum in between x 1 and x star, alright. And in the next case, when f x star is greater than f x 2, there is no minimum in between x star and x 3. Okay. After elimination, what we will do? We will again go back to the step 1, because we are defining new interval of uncertainty. We are defining the interval where the left points we are considering, we are redefining, right hand point we are redefining, and we are having another point in between as well. Again we will repeat the process. Let us see with the example the same thing. This is the function, and this is the function rather, as I showed you previously, alright. And we found the value for a naught is 20, a 1 is minus 41.4894, and a 2 is 58 point. This is after solving these 3 equations only we got it, because there are 3 unknowns and 3 equations. From here we are getting the values for a naught. Once we are getting the value for a naught, a 1, a 2, then we can say what is my p x then? P x must be is equal to 20 minus 41.548 or so x plus 58.3369 x square. This is my polynomial. I have drawn the polynomial, just you see, with the blue. The red is the function and blue is the fitted polynomial. I hope you are not really satisfied with this polynomial, because this is not fitting function very nicely, and if I want to get the minimum of this polynomial, then we could see the minimum of the polynomial is 0.355, okay, and that cannot be the desired minimum at all. That is why it is not accepted. Okay. We are going to the next. How really we have checked mathematically entire thing? We found that x star is equal to this, f x star we calculated, p x star we calculated, and we were testing f x star minus p x star divided by f x star is a large value, that is 0.08. We expect the value must be 0.0001 or like that, then only we can say this is a good fit, otherwise not a good fit. That is why we have decided we will go to the next iteration. Once we are doing that, we could see the value for function is 20, here is 13, here it is 1, okay, and at the x star the value of f x star is coming 13.728. That is why we can say that x star is lesser than x 2, lesser than 0.5, f x star is lesser than f x 2. That is why there is no need to consider the interval 0.5 to 1, because there cannot have any minimum. Okay. Function is unimodal within that. That's why there cannot have any minimum. That's why let us consider the new interval of uncertainty as from 0 to 0.5, all right, and the value, the new value x star we have considered as the next point, not the mid value of these two endpoints, all right. Then if we have again 3 equations with 3 unknowns, how really? Because in the next iteration this is my x 1, this is my x 2, this is my x 3, we will just substitute in the function here like this. We are having the polynomial p x is equal to a naught plus a 1 x plus a 2 x square. Then if this is so, then a naught plus a 1 into 0 plus a 2 into 0 is equal to 20. A naught plus A1 into 0.355 plus A2 into 0.355 square is equal to 13.728. The third equation is A naught plus A1 into 0.5 plus A2 into 0.5 square is equal to 13.8395. That means, again we are getting 3 equations, 3 unknowns, and we will get the values for A naught, A1 and A2 from these equations. These are the new values of A naught, A1 and A2. All right. That means, we are getting another polynomial. What is that polynomial? Polynomial is 20 minus 30.728x plus 36.81x square. This is my polynomial. Let us see whether this polynomial is fitting the function or not. For checking that thing, you need to find out the x star value. What is your x star value? That is equal to minus A1 by 2A2, and we need to find out that Fx star minus Px star divided by Px star must be less than epsilon. Okay. Then only we can say that if the epsilon value is very small, then we can say that this is a good fit. Just we found for these values it was coming 0.007 or so. Okay. We got that value. You can calculate also. All right. And if you calculate this value, if you are happy, you can stop the iteration. If you are not happy, again you can go for the region elimination technique and you can get the better polynomial. But if we just look at the graph of it, that here the red one is the original function and the blue one is the fitted polynomial. In the first iteration, that was the fitted polynomial, and in the second iteration the blue is blue and red, just to see, all are almost mixing together. If you just zoom it, maybe you may not be satisfied with that, but at a glance if you are satisfied, you can stop the iteration here. All right. Here since the value is 0.007, you can stop. Okay. In this way we just do the quadratic polynomial interpolation, but if we want to do the next, if we want to just interpolate a cubic polynomial there for the same function, that also we can do. How really we can do it? We will take the polynomial as A0 plus A1x plus A2x square plus A3x cube. All right. Now we are having 2 points 0 and 1. Okay. For finding out the values for A0, A1, A2 and A3, how many points you need? You need 4 points, then only you will get 4 equations. With 4 unknowns, you can find out the value for A0, A1, A2 and A3. And again also we can have x1, x2, x3, x4, and if I just proceed in this way, then we can again fit a nice cubic polynomial here like this. Okay. That is all for today. Thank you.